Hi everyone. So this is lecture 20 on the Jupyter Notebook and on doing integrals using some the Scipy optimize. So this lecture is going to be a little different. I'm not going to write today. As you can see, I'm going to be using this Jupyter Notebook, which I'm going to explain in a second. But our outline is here at the top. So the first thing we have is I'm going to cover Jupyter Notebook, this platform I'm using. Then I'm going to talk about using the Sympy.Integrate module to do numerical integration, which is what we talked about last time. This time we're going to learn the Sympy functions for doing it. And then finally I'm going to talk about doing some symbolic calculus. This is kind of a little extra bonus thing. We have a little bit of homework problems on it, but this is more just to show you what that is, to give you that option of using it when it's useful for you in other classes. All right, so let's dive right in. So the first thing I'm going to talk about today is the Jupyter Notebook. So Jupyter is basically another way of interacting with the Python language that in addition to Spider. So we've been using Spider all class. That's sort of what's called an integrated development environment. It's a place where you can type in the code, you can execute the code, you have a debugger, this sort of thing. Jupyter is a little different. It's a notebook. A notebook is a way to sort of organize both code and text and pictures and maybe even video and implement them all together and make them pretty. And a lot of your professors that teach that use Python ask you to do things in Jupyter. So I wanted to give you an opportunity to see that. And also, I just think it's a neat tool to see. But just like Spider, you use Jupyter to edit Python code. And in the same thing that you installed, when I gave you installation instructions, you can go back and see that video earlier about how to install Python using Anaconda. Anaconda also has a Jupyter Notebook. So if you go ahead and go to that spot, you can find it on your computer and open your Anaconda Navigator. You can open up Jupyter, and actually it'll open in a browser. So whatever browser you use, I'm using Chrome here. It'll open in a browser and it'll look like this, right? And depending on what the path where you opened it, you're going to see the files. And notice that instead of just .py files, these give you .ipynb. So these are IPython notebook files. So they're a little different. If you just open them with a text editor, they've got all sorts of gobbledygook in them in addition to the Python code that's in them, because they're formatting themselves in this way. So Jupyter stores them as a .ipynb file. Okay. So the first thing to say about a notebook is that a notebook essentially consists of these cells, these little regions that you can see the box around. All right, and each cell has a different type that it can be. Okay, so if you go up here, you can click, you can see the different type of cell. All right, and so these are all markdown cells. So you can see if I double click on it, what I'm actually typing into it. Okay, and I'll make that go away for a second. All right, but so there's three different main types that we'll be using. There's a code cell. All right, a code cell is something that has Python code in it that you can execute. A markdown cell is like this. A markdown cell you can kind of think of like a text editor like Word, except we'll talk about it in a minute what markdown is. But basically it allows you to do formatting and type nice stuff up. Okay, and then there are raw cells if you just want to have plain text that isn't executable, it isn't markdown. You can have a raw cell. Okay, you can insert and delete cells. So if you come up here to edit, you can copy, paste. You can come here and insert a cell above. So if you do insert, you can insert that cell here. Notice that it's automatically code. I can change it to markdown. I can change it to heading. Okay. This says Jupyter no longer uses headings. That's fine. All right. You'll actually just use markdown, or you can have a raw cell. All right. The two most common are code and markdown. All right. Then if you don't want to have that cell anymore, you can come over here to edit and click delete cells, and that'll delete the cell. You can execute the cell by clicking on this run button right here. That'll run the cell. Notice for markdown cell, it doesn't run anything. And you can edit the cell by double clicking on it. so that will show what's inside here. If you've already double clicked on it, you can click run and it'll go back, okay? Or you can click shift enter, so you can't see my hands, I'm doing shift enter, or if I double click on it again, you can do control enter, all right? Note that cells are aware of all the other code in the document. So if this were a code cell and this were a code cell, then I would have the variables from the cell above will be known by the cell before. So I'll say more about code cells in a second, but let me just add a cell below here. So if I hit Alt Enter, that will add a cell below. So suppose I define x equals 4, okay? And then I define another new cell down here that says print of x. Okay, if I run this one, I click run, that assigns x to 4. If I print x, that will print x right there. All right, so these cells, they know about each other. And you can totally wipe the slate clean if you come up here and click restart on the kernel. So if you do that, it's going to delete everything, okay, and it'll start over. And now if I run down here and do print x, it says, I don't know anything about x. Okay, there's an easier way to do that. At the beginning of a cell, you can type the % reset. So if I do this, x is 4. If I don't do that for a second, I print x, now it goes back. If I put in reset, it will delete all the variables. And it'll say, yeah, do you want to delete them all? Yes. And then it freaks out because it doesn't know about it. If instead of deleting all the variables, I just want to do one, I can do del x. And then now x is deleted, and it won't know about x either. Okay, so that's just a little trick. I'm going to highlight both of these cells, which I did by shift and click, and I can come up here and edit delete cells. Okay, so that's a little bit just about cells in general. So let's talk about the different kind of cells. So there's code cells, which I've just been using. In code cells, you write in Python. So here is an example. This is a markdown cell. This is a markdown cell, and we'll talk about those next. Okay. Shift enter, shift enter. All right, this is a code cell. When I double click on it, it doesn't do anything else. It looks the same. And you could just copy and paste code from Spider into here and it should run. Right, so here I'm importing NumPy and Matplotlib, and I set up variables x and y. X goes from 0 to 2 pi. Y is a sine of x. And then I make a plot. And when I run this, let's see. Okay, there goes. So I run this, you notice that one of the nice things about it is that it shows my output immediately below the code cell. So maybe you noticed this when I did the print before. It just prints it right below. So this can be a really nice way to organize homework problems, for instance, which is one of the reasons why professors in the department like to use it, is they'll say do number 1, and then you'll print stuff, put whatever you want. You can scan a picture and put it in if you had to do something by hand. Okay, and then you can make a code cell and print out your answer, and voila, you have the whole thing. Okay, so this is a really nice feature about Jupyter. I personally think that it's a little harder to debug. Okay, because you have to, you don't have a debugger, and you have to do more of the sort of run, and run these little segments to check it. But it's not like it's impossible to debug. But I think when you're brand new, it's a little harder. That's why I teach you in Spider first. But I love Jupyter. I think it's a great tool. Okay, so the next kind of cell are markdown cells. So markdown is a little markup language. It's like HTML, if you know anything about HTML. Actually, you can use HTML inside markdown, so any HTML commands you can just put in there. And so if I double click on this cell, this is a heading, all right, and the level of heading has to do with how many pound signs. So I put a pound sign and then a space, and that will make that big and bold heading. If I come down here, I can click on these. You can see how I do links, all right. So I'm going to go through a couple examples of just how to do this, but basically it's a way of typing in text kind of how you think you might type text to look formatted, and then it automatically formats it for you. So for instance, if you come down here, if you want italic text, you put single asterisks around it. Maybe you've done that before when you're texting or something. Put an asterisk around something to highlight it. If you put 2, you get bold. All right. You can use HTML code, like I said, to make something green. And hyperlinks, you start with square brackets and then put parentheses around them. And that makes hyperlinks. So that one's formatting's pretty easy. I just told you about headings. Okay, so headings, you proceed with the pound sign and a space. Don't forget to do the space. If you forget to do the space, it's not going to work. Okay, it'll just print out like that. So you got to put the space in there. All right, and each successively further down the chain of headings that you go, you put more pound signs. If you want to make a new paragraph, you put an empty line in between. If you want it to be on the same line, you don't put anything. Even if you type it on a new line, it'll connect it. So if you want a separate line, you put a couple spaces, 2 spaces at the end. Then you run that. Now it gives it a new line. All right. So that's text, headings. Okay. Lists are super easy, I think. So in a list, you just put a single asterisk and a space, and that's going to add a bullet there. And if you want it to be indented, you just tab over and put another bullet. Okay. And that will make a sub bullet. You can make a sub bullet if you put it over 3, okay? And you can see it makes the different round, square, open circles, etc. All right. If you want to make a numbered list, you just start numbering 1 dot space, 2 dot space, okay? And it'll actually do outline sort of format for you. So if you do 1 here, it'll start doing A in the next one and a little a in the next one, as you'll notice, even though I'm counting with just 1, 2, 1, 2. Right? So it goes ahead and figures that all out for me. So that's really nice. A little bit more advanced, but not too much more difficult, is to do math in a nice formatted way. So maybe you've noticed this. You're sending around emails, you're asking me questions, and you want to put math in there, and it's really kind of messy and ugly. There's a little language for typesetting math called LaTeX, LaTeX. Okay, that's called LaTeX. It's not latex. That's what people call it. Don't ask me why. I don't really know. The basic idea is that you put dollar signs around the math, and then there's a couple different kinds of symbols that you can sort of type out, and that will then translate that into prettier looking math. So you put dollar signs around your math, A equals B, okay, and that will print out, A equals B in a prettier way. So here's a nice example. You put in dollar sign A squared plus B squared equals C squared, and that does this. And you put the little hats like you do in Excel for the squares, and that actually raises them and does this. If you put 2 dollar signs around it, what happens is this will this makes an inline equation with a single dollar sign. 2 dollar signs gives you an equation on its own line in what's called display format. All right. So you can do all sorts of things you can play around with. I'll just highlight a couple. If you want to know more about this, click on these tutorials or cheat sheets and look at them. It's not super important to me that you know how to do this, but I want you to be introduced to it. Okay. So the idea here, you can do fractions by this \frac, and then you put things in curly braces to put what's in the numerator and denominator. If you want to put more things in a superscript, you have to put them in the curly braces. If you want to do subscript, you use an underscore. And if you want multiple characters, you put them in curly braces. You can give yourself a space in math. So you might notice that even though I added a space, it puts them together. It's typesetting that on its own, but if you want to force a space, you can put a slash comma. You can do things like partial derivatives. There's a special curly D for partial, if you've ever noticed in math. So you can do this slash partial. It's not a delta. A lot of students, when you're very first learning that, think it's a delta. It's actually not a delta. It's a special curly D. And then there are all sorts of special functions that you can do in Greek symbols. So if you want to do alpha, beta, gamma, delta, whatever, all right, you can just use this slash gamma and it'll insert a gamma. So you don't have to do the thing in Microsoft Word where you go look up the symbol or find out the Unicode and have to type it in by hand or whatever. Okay, so and you can do all sorts of nice things with parentheses, and it can get fancy and complicated. And this is really valuable for making your math pretty if you want to do this in the thing. Okay, so that's a really quick 10-minute introduction to Jupyter. I hope you take a few minutes to play around with it. You're actually going to be required on this homework assignment associated with this lecture to do that in Jupyter and turn it in so that you get a little practice doing this. Okay, so that's one Jupyter Notebook. Okay, so the second thing is the more numerical methods part of the class that we've been sort of going along and if you recall last time in the last video, and if you didn't watch it, go back and watch it, but we talked about doing numerical integration. And we talked about how you had to interpolate a function, and then you got a polynomial from that, and you integrated that. Okay, so that's a lot of work, right? You have to figure out that method. You have to code it in yourself. It's not too hard. You just have a couple loops, and I'm sure that you figured that out by now. But it's a pain to have to do that every time. So Sympy has built-in functions to do numerical integration, just like we have special functions for doing other things. And we're going to learn two functions today. We're going to learn a function called quad, and we're going to learn a function called Simps. And both of these are inside the Sympy.Integrate module. So if you recall, we've learned a bunch of other modules in Sympy. We've learned the optimize, and we've learned interpolate. Okay, so now we're adding another one, integrate. So we have optimize, interpolate, now we have integrate. And hopefully you can remember integrate because we're doing numerical integration with Sympy.Integrate. Okay, and like I said, there are two methods or two different functions that we're going to use, and they're useful in two different circumstances for the following reasons. So the first one is called quad. Okay, remember we learned that quadrature is another word for numerical integration, and quad is if you can use it, it's the best function to use. Okay, it's the most accurate, it's the fastest, but it has a limitation. All right, and that limitation is that you actually have to know the functional form. So you have to know something like x squared, that you're integrating x squared. All right, and it turns out that quad uses a method we didn't learn. It doesn't use a Newton-Cotes formula. It uses what's called Gaussian quadrature, and Gaussian quadrature doesn't use linearly spaced points. And so it has to pick where it wants to evaluate it, and so it needs to know the whole function. Simps is the other function that we're going to use, and in Simps you can have the whole function if you want. You can know that it's x squared, but you actually don't need that. All you need is the data points. So just like in interpolation, you only need the data points to know where that function is. Simps also, if all you have is linearly spaced, regularly spaced data points, you can plug that in and get an integral of that. Right? So that's useful. So you might think, well, what's the difference between here, right? So if you're doing a problem and you say you have a function for the heat capacity, great. You can take that function, you want to integrate it and put it in. You can use quad and do that. But suppose you have something like flow rate out, and you have a flow rate meter out of your tank, and you want to know what the total amount of volume that you've taken out of that tank with respect to time. There you don't have any function to use. You just have some data points of what the flow rate is, right? And so there you're going to use Simps to be able to do that integration. Okay, so let's dive in and see a couple examples of how to do this. So the first one I'm going to start out with is quad. Notice that there's a link here for the documentation. I highly recommend you just click on that link, check it out. So what's going on here? So what you're going to have to do is you're going to have to import quad from Sympy.Integrate. All right, that's the first step. Then you're going to have to define your function somewhere. So that's the function that you're going to integrate. That's going to be given in the problem. Then the last thing you do is just have to evaluate the integral by calling the function. And it returns actually a tuple. It returns the value of the integral and an error. And you assign that to quad, and you need to give it the function name. All right, so that's the actual thing the thing that you defined. Okay, and then you need to give it the lower bound and the upper bound for the integral, and that's it. Okay, so let's see our example here. So I'm going to evaluate this integral. I is equal to the integral from 0 to 1 of 3x squared plus 1 dx. All right, and I happen to know that the exact answer is 2. That's not super hard to figure out because this is polynomial, so you can probably prove that to yourself as well. All right, so let's see how to do that. So here I come down, I do my 3 steps. My first step is to import from Sympy.Integrate. I want to import quad. All right, and then I define my function, which I'm going to call f of x, and I define that function as 3x squared plus 1. For some reason here I must have, I did it x times x. That's the equivalent to doing x squared, right? And then I define the bounds of this integral. The bounds are from 0 to 1. So I go 0 is my low, 1 is my upper bound. okay? And then I know that's going to return a tuple of these two values, the integral and the error. So I actually do this 3 times to show you something about this. Let me comment these out for a second, and I'll show you that in just a second. But so I call I from quad, and then I have the error, and then this calls quad. Notice that this is f. This isn't like f of x, all right? Because I'm just giving it the function handle, just the name of that function. I haven't called it on anything. If I call f of x, it's going to go looking for an x to evaluate that function. I don't want to do that. All right? Then I give it the value of the low and the high, and then I'm going to print out the error. Okay, print out the value. So it goes ahead and runs. All right? And notice I didn't have to tell it how many points to evaluate. I didn't have to tell it anything. I just said evaluate it. All right? This is a super easy function to use if you know f. Right? And look what it did. It gave me an answer of 2 with an error of 2 times 10 to the minus 14th. That's spectacular, right? I don't know if you remember from last homework when we were doing things with Simpson's rule or trapezoidal rule, all right? But those were nearly as accurate, all right? So this one is really super accurate. So now you might be like me and you don't always want that error and to save a variable for that. So what I'm showing in these other quick little examples is that if you don't want to save the error, you can actually put an underscore here. Underscore is like a value in the notebook that just stores it as like the most recent thing. It's like the value of the last thing it printed out. And so it just sort of dumps it into there, and then you don't have to worry about it anymore. It'll just get erased, okay? If you don't want to even store it, what you can do instead is you can return just the 0 value of that tuple. So you call quad, and it's going to give you back a tuple that has 2 values, and you can say, I just want the 0, right? It's got a 0 and a 1, and I'm going to assign the 0 one to I quad and just neglect the error. This is the one I kind of prefer to do because it's really clean, and then I don't even have to worry about putting a comma underscore. You can pick what you want to do. So now if I run this, note that the error was defined in the previous time. This is one of the tricky things about Jupyter. So if I keep running this, right, it's going to keep telling me an error. But notice I can do what I did a couple things ago, and I can delete error. Okay, now I run this. Now it gives free sound. It says I don't know what error is, right, because I deleted it there. All right, so make sure that you're careful when you're running Jupyter to know what your variables are and how they're connected. Okay, that's one of the most common errors I see in debugging is you run something up here that was important, and then you come down here and run this and change this code, and you're like, why is it broken? It's not working, and it's because it's up there, right? It's up in that other code. Okay. All right, so that's the quad function. What about the Simps function? So Simps, if I didn't say this already, I should have. It integrates using Simpson's rule, and you know Simpson's rule, so great. You should be able to even just code that and check it for yourself. But this does it for you. Okay, and the steps are pretty similar to quad, but there's a little bit of difference in how you call the function, and it has to do with this difference in that quad needs a function, and Simpson's rule does not need a function, it only needs points. Okay, so the steps are you need to import it from the Scipy.Integrate module. Check, that one's easy. Okay, then you need to either read in or define your x and y data. So instead of defining a function, you have to define 2 arrays, an x array and a y array. All right, and then the last thing is you evaluate that integral. And the way you evaluate it is you say the value of the integral, this is like our I, is equal to Simps, and then you call y data comma x data. All right, so here you're doing this is the function that you're integrating, but you don't know what it is. It's just the data, and an x is the points over which you're integrating it. Okay, so here's an example. So we're going to integrate the curve defined by these points here. This is actually the same problem that you had in your homework last time. That should give you 2 over 3 pi. I just have 10 or 11 data points here. Looks like 10 data points that we're going to integrate from. So what do? I import Simps from the Scipy.Integrate module, and then I define this data. This data is given in this problem, okay? If you're given a function, I'll show you in just a second how you can go about doing that if you're given a function instead, but you're told to use Simps. Generally, if you're given a function, you'd use quad, but for the purposes of homework and practice, it's good to know how to use Simps even if you're given a function, just to sort of figure that out. All right. So then what do? I go down here and I call the integral is equal to Simps y data comma x data. All right. And then I just print out. Notice that it doesn't give me an error. It doesn't know about that. If I want an error, I have to estimate it myself. So I run that here, and you see that the integral is 0.211, which has a pretty good error, right? Around 10 to the minus 3. That's a lot better than the trapezoidal rule had, but it's not nearly as good as the Gaussian quadrature. All right. So Gaussian quadrature is awesome. Quad's awesome. Simps is great when you need it. Okay, and it's certainly nice enough to be able to code it yourself. All right, so let me show you really quick. So there's this example practice worksheet that I've uploaded on the web that you can check out. And the practice worksheet has a bunch of different things you can play around with. One of the things it has is a place to do a practice integral. And I advise you to go through and do this practice on your own. I give you both the practice and the key. I'm cheating and showing you the key real quick just to show you this quick idea. So if I want to do Simpson's rule and I'm given the function here, f of x, okay, if I have my x points that I've already defined right here, I have my x points. I can just call my function of x, all right? That's going to evaluate as a bunch of points. So I can show you what that looks like, right? I know if I print x and I print f of x, look, that prints for me 2 arrays, all right? So now I can just plug those right into Simps. So if you're given a function, it's pretty easy to call the Simpson's rule function, but obviously, as you see in this example, the quadrature, Gaussian quadrature method is way better. Okay, so that's an example. You should go around and play with this practice example if you get a few minutes. And as a matter of fact, right now would be a great time before we move on in the last section to just sort of pause the video, pull up the practice. At the beginning of the practice, there is just some stuff to mess around with Jupyter and to make some plots, just to sort of get yourself familiar, and then you can go ahead and work through this example doing quadrature, and I think that'll really help you out if you do that. So why don't you go ahead and pause and do that, and then I'll resume with the last part. Okay, so hopefully you've done that. So let me move on to the very last thing I'm going to do. This is sort of a bonus thing. You do have some homework problems on it, but this isn't something as important as being able to do integrals in numerical method. And that's using Jupyter and Python to do symbolic math. All right. So symbolic math is the kind of math that you do by hand when you're sitting down on a piece of paper and you do x squared plus y squared equals whatever, and you solve the quadratic equation. All right. And you can do exact manipulations that way, and sometimes it gets messy and painful. I don't know if you've ever had to expand a quartic function or something that's really obnoxious to do, and so it's nice to be able to have a symbolic solver around. There's lots of these that exist. Maybe you use Mathematica or Maple. I personally use Mathematica quite frequently when I had to do this kind of stuff. But Python also has a really a powerful symbolic math tool. All right. And there is a module for doing this that's called Sympy. At least I call it Sympy, sort of in analogy with NumPy. All right, Sympy stands for Symbolic Python, and the way you import it is by doing import Sympy as SP. Okay, you can call that as whatever you want, but SP is pretty useful. It's nice and short, and like I said, it's sort of like NumPy NP. It's SP. And then you need to call these two other pieces when you do it. You need to do init printing, which will make the output that it prints out a lot better looking. You can play around, uncomment it, and see what it looks like without it. And you need to import this display function that you use to display instead of doing the print function. So if you do print, you're going to get ugly output, but if you do display, it'll give you pretty output. So I'm going to run both of those guys. And what you do in Sympy is you define a symbol. So in this case, I'm defining 3 symbols here, x, y, and z, and they're comma separated. but I could just define 1 if I wanted for a moment. If I do x is equal to sp.symbol x, all right, and when I run that, okay, and you notice it has some errors because I didn't define y and z. What it's doing is it's defining an x symbol as this variable x. Okay, these don't have to be the same thing, and I'm showing that right here. So if I want to define something as a symbol L, I can name the variable ELL for L. Okay, and what I'm showing in this one is I can actually define multiple symbols at the same time. So I can define x, y, and z, right? And then I want to call that display function that I just pointed out here instead of print. So when I display x, notice I have this nice pretty x. I display L, I have a nice pretty L. And then what I can do is I can evaluate an expression like x times cosine x, and I can make that this new variable expression 1. All right. Notice that I used the same multiplication symbol that I used to do before. And when I want to do something like cosine, instead of numpy.cosine, I do sp.cosine. All right, and that gives me x cosine x. And I can do all sorts of other things, any other math function that you think you can do. Now it makes up these expressions, right? And now what you can do, once you've defined these expressions and variables and symbols, all right, you can manipulate them doing algebraic manipulation and other kinds of calculus manipulation. So I'm going to show you that over just the next 5 minutes or so. Okay, so the algebra manipulation that you can do is I think really useful if you've got these sort of big hairy expressions, but it's useful to break them down into these sort of small simple things. And essentially they have different functions that you can call on these expressions. So if I define a function x cubed divided by x squared, it's really obvious what that simplifies to, but you can call the sp.simplify function on that expression and it'll reduce it to x. All right, so it does that cancellation for you. So you could also imagine having a big hairy function that it's not obvious what cancels. You run simplify on that big hairy function and it cancels it out for you. Okay. You can also expand. So this one maybe is a little more obvious why that's useful. You can keep adding pieces here, right? So I have x squared or x plus 2 times x minus 3. Okay, I can expand that pretty quick. But if I also do x plus 4 and x minus 5, that's pretty easy to type. But if I go ahead and run that, when I do Sympy.expand, boom, it expands out that whole quartic expression, and I don't have to do that all by hand. So that's a really nice thing to be able to do. Okay. Another function is factor. So that also maybe you've is not always obvious to do. So you type my expression here, which is this cubic function. I type Sympy.factor of the expression, and it returns the expression factored out. Okay, so there's sort of 3 simplification algebraic manipulations. A really powerful one is substitution. So I can take this, I define my expression as x cubed plus x squared plus x minus 1, and I call, now notice here that I'm taking that expression, ex, as the dot. So this isn't Sympy dot, this is the expression dot, okay? This is kind of, in a way, I almost hesitate to say this, but you can maybe think about this way at the beginning. This is kind of like defining a function and then evaluating the function. It's not exactly like that, okay? It's substituting this in here. But what this is going to do is going to substitute a numerical number into this, all right? And then when I go to display, it'll return the value that it evaluated out of that, okay? The reason I hesitate to say that it's like a function is because it's not a Python function at all. And if you tried to use this in something like our quadrature or Simpson's rule or whatever other methods we've been using before, it's not going to work, okay? So don't use symbolic math mixed with our numerical methods that we've been doing. This is sort of a separate thing that you can do to do some algebraic manipulation, all right, that's separate from defining the variables you're going to use to do numerical methods, okay? So notice that if I put in a 2 point, it's going to evaluate this as a floating point number. If I put in a 2, it's going to treat this 2 like an integer 2, and it'll actually evaluate that symbolically, okay? So, if I put in 2.14 here, it's going to, evaluate this numerically. It's just printing it prettier, okay? So substitute is really useful for both expressions, and you can also substitute in other variables, all right? So here I had x cubed plus or minus x squared plus x minus 1. I could substitute y, and I get an expression here where I just have substituted y for x, but I could also substitute y squared plus z, all right? And when I run that, I get, this big old hairy expression. And suppose I wanted to expand that, I could do, let's try this on the fly, Sympy.expand of this guy. And do I need something else? Let me just, no, I don't think I do. And I run that, and notice now it's expanded out all the terms for me. Okay, so you can combine these expressions together, substitution and expand, and that might be something, that would have taken you a long time to plug that in, cube it, then square it, then add it, simplify it all together, and look, it did it all for me. Okay, so that's a really nice thing that it can do. Okay, there's many more algebra functions that you can do. You can all sorts of things. You can do matrix math, you can find eigenvalues, you can solve linear and nonlinear symbolic expressions, etc. I'm not going to go into this. This is really just meant to be an introduction to symbolic expressions that you can then play around with and use at your own on your own time and when it suits you. Okay, so here's the links up at the top here for the tutorial and the documentation. I highly recommend you at least click on the link and browse around for 2 minutes. All right, now would be a great time to pause the video and do that, just to familiarize yourself with this. Okay, the last thing to talk about is some of the calculus functions that it can do. If you're like me, looking up integrals in a table can be painful, and you're not always sure exactly, you have to sit down and be really careful as you substitute them in. So it's really nice to be able to have a solver like, or a symbolic tool like this to be able to do some integrals for you. All right. So what we're going to learn here really quick is the functions for derivatives and integrals. Right? So suppose I define an expression e to the x to the fourth. Okay. I can then do sp.diff. And diff is the expression for the derivative. And if I just do diff and I do with respect to x, that'll just take a single derivative. Perfect. But I can do higher order derivatives if I want. So if I did a single derivative, that gives me 4x cubed times e to the x to the fourth. But suppose I wanted to do the third derivative, of that guy. Well, it turns out diff makes it really easy. You just put another comma, put a 3. Now it takes the third derivative. Okay, that's really nice. But diff is even more useful than that. If I want, I can take partial derivatives. Okay, so I can take the differential of the x of this expression here, and let me just for a moment make it with respect to x only. Okay, and it does the partial derivative with respect to x. I can do the partial derivative with respect to y, and I can do the partial derivative with respect to x and y. Okay. And so that gives me, this expression. So differential is, diff is a super valuable, function that basically you can use to do any sort of complicated derivatives that you want. All right. The last thing I'm going to point out is integral. This sp.integrate allows you to do symbolic integrals. So in sp.integrate, suppose you want to integrate x squared. What you need to do is you need to give it the expression and then the variable, and that will do an indefinite integral, right? That's ones without bounds. Notice that it doesn't tell you you have a constant at the end. It assumes you're smart enough to know that you have a constant going on, okay? So you have to be careful to do that, all right, to know that by yourself. So if you go ahead and do this for your calculus homework and you get it wrong, don't blame me, okay? That's on you to remember that you have a constant. But it can also do definite integrals. So if instead of just putting the symbol, okay, that you're going to integrate with respect to, you put in the symbol and you give it 2 bounds in a tuple like this. This is your lower bound and this is your upper bound. Now it will numerically evaluate this. And of course, if this is our expression going from 0 to 1, I'm going to get 1/3. Okay, I could go from 0 to 2, and I should get 8/3, and I do. Okay, so you can see that this allows me to do a definite integral. And you can even do improper integrals where you can put things like infinity. So here I'm integrating e to the minus x rather, from 0 to infinity. And Sympy has this really fun infinity function. You just value for infinity, you do sp.oo. Okay, this is 2 little o's. And that's infinity. So it kind of looks like the symbol for infinity. I'm sure that's where they got it. All right, and so that will evaluate this to infinity. Or if you want, you can use other symbols. So if you want, you can plug in y here. So I have x e to the minus x. Now I'm going to integrate, instead of from 0 to infinity, I'm going to integrate from y to infinity. Okay, so you can do all sorts of things with this. Again, this integrate function is really valuable. It's like having a integral table in your pocket to be able to do any integral table that you want. Okay. Okay, so there's other calculus functions. You can solve differential equations, which we're not going to cover in this class. You can do Taylor series if you want to expand something. You can do finite differences, which we're not going to talk about in this class, but is something you might encounter in numerical methods later. All right, so there's all sorts of super valuable things you can do with these functions. Okay, so that's all I have planned for you. If you haven't already, I'd highly advise you pop over and check out the example problems that I've given you. There's an example problem for the notebook, for Python, quadrature methods for quad and Simps, and for doing symbolic math. I highly recommend that you sit down and play through those. Your homework is all on this, and there's a worked out key that you can download on the web. With that, I would just thank you for listening, wish you good luck on your homework, and hope that you have a great day.